All right, so let me, all right, so let me say a couple of words about the next homework, which is due after the break. Um, maybe later than that. Don't ruin your, I say break doing, I mean, if this is a great way to spend your break, you go ahead, but, number one, prove that every overring of a valuation domain is in fact a localization, right? And like I pointed out before, having this property that is every overring is a localization is actually a pretty rare gift. This isn't so difficult, I don't think, to show, so prove that. For problem two, so the focus of this obviously is valuation domains here. For number two, I globalize valuation domains in the following sense. Valuation domains are always quasi-local. I'm going to globalize them. We say that an integral domain is a proofer domain if R localized at P is a valuation domain for every prime ideal. So if you have a domain and you localize it every prime ideal, it turns out to be a valuation domain, we call that a proofer domain. But it is sort of the global version. It is locally a proofer domain. Or I'm sorry, it's locally evaluation domain. So number two, let R be a proofer domain. Show that R is a proofer domain if and only if R localized at M is evaluation domain for each maximal ideal. So in other words, you don't really have to check all the prime ideals. You only have to check the maximal ones, and that'll be good enough for being a proofer. Show that any overring of a proofer domain is a proofer domain. And actually that should follow from the next one. This one's one of my favorite little theorems about proofer domains. Let R be an integral domain. Show that R is a proofer domain if and only if every overring of R is integrally closed. One direction of this is not too difficult. For the other, so here's a hint for one of the directions. Consider R localized at M for some maximal ideal, and if X, Y is in R localized at M, consider this ring here, where you take y squared over x squared and join it to R and M. So play around with that. That's a fun little problem. So this will make a lot more sense today when we talk about how, so I've been talking about valuation domains, right? And what's a valuation? Well, I'm going to tell you what that is today. And in fact, this is the definition here. Let R be a domain with quotient field K. We define the group of divisibility of R, which I'm going to call G of R, to be, it's a multiplicative group. Take the non-zero elements of K and mod out by the units of R, right? This is a group, right? So for example, with the integers, right, you take the rational numbers, take the non-zero rational numbers, and mod out by the units of the integers, which is plus or minus one. So basically the group would be isomorphic to the positive rationals under multiplication. But this isn't just a garden variety group, it's got some superpowers. In fact, what it has is a partial ordering. So there's a relation on, which I'll call less than or equal to, on the group of divisibility that is reflexive, transitive, and antisymmetric. And this relation is given by, we say a coset A times the unit of R is less than or equal to B units of R, and that's supposed to be an if, I'll fix that, if B over A is an element of R, right? So, for example, if you look at the integers, not every two cosets are comparable, right? So, for example, in the integers, notice that every integer is comparable to 1, right? Because integer divided by 1 is an integer. But for example, 2 and 3 are not comparable, right? Because, well, neither 3/2 nor 2/3 is an integer, right? So now that we have this group of divisibility, show that the group of divisibility is totally ordered if and only if R is a valuation domain. And number B, show that V is a valuation domain with quotient field K if and only if there is a function. This is valuation. We're going to talk about this a little bit today. A function from the non-zero elements of K to G, where G is some totally ordered abelian group, satisfying the valuation of A times B is V of A plus V of B, and the value of A plus B is greater than or equal to the min of these two, and that should be a plus here. I have got two typos there. I got to fix this. This should be A plus B. It's not zero because this isn't defined as zero. So anyway, have some fun with that. Let me know if you have any problems. Ready? Huh. Strangely uncooperative. Okay. Any questions? Okay, so the last thing we talked about was this this business about ideal survival. So let's recall briefly that when I survive in and that's what we proved at the end of our last meeting. And here I am going to bootstrap this into a theorem and use that to bootstrap into the next theorem. This one is very interesting and important. Let's see, this is theorem 415. That R being the domain with a quotient field and I and R a proper ideal. And there exists a valuation of such that I survives in Z. Okay, so this is kind of a groovy little theorem because what it says is if I've got an ideal that survives, so it's a prop, if I've got an ideal in R that's a proper ideal, then there is some valuation overring where this persists in being a proper ideal. Somewhere there has one. Any ideas on how we might go about?
We take the maximal ideal contained in I and localize at
that? Actually, that's a pretty reasonable strategy. Of course, here's the problem. Certainly I is contained in a maximal ideal. In fact, one might expect it to be contained in a whole lot of them. But R localized at M, I don't expect to be a valuation domain. Right. So I'm gonna have to go up a little bit further than that, probably. Right. Although I could see sort of a computational, maybe one could start there and, you know, sort of build something. I think eventually we'll have to do Zorn's lemma. So here's the idea. Maybe I shouldn't put proof here yet because more sort of outline idea. Find maximal overring of R in which I survives. Right? Now, this is kind of, so I'm kind of, before I get into the proof, I'm going to kind of describe the strategy. I know that I survives an R, right, by hypothesis. So let's see if we can find a maximal overring in which this survives, and cross our fingers very hard and hope that such a maximal overring where it survives has to be valuation domain, right? And so this is the strategy. So let's do this. Now, of course, when I say that I survives, I is a set of elements in R, and it's got an analog. I has an analog in a larger range, but it's not the same set. So what I'm going to do is I'm going to consider pairs. Let's call it Ri and, well, let's call it Rj and Ij, where so Rj is an overring of this, and Ij is a proper ideal such that I is contained in Ij. So R is an overring and I is some ideal that is proper, right? It can't be the whole ring, that contains I as a set. Okay. So in particular, what this means is if you look at IRJ, this is contained in IJ, which is strictly contained in RJ. So in other words, this it just assures us that I actually survives as an ideal of RJ, right? Okay, so this is the idea here. So let's let gamma be set of such ordered pairs. Now, I bet you can smell what the rock's cooking here, right? I'm going to try to get a maximal such thing. So to get a maximal one, I need some kind of partial order here. So that's perhaps the question. Gamma is a coset where I'm going to find the order RJ IJ is less than or equal to RJ prime IJ prime.
Pointwise conclusion, so they're both.
Okay, yeah. If and only if RJ is contained in RJ prime and IJ is contained in IJ prime. Right, it's sort of like a product order thing. That's right. Now, of course, I expect this to be a very partially ordered set in the following sense, right? You might, even if these two rings are exactly the same, which is a possibility, these could be two incomparable ideals that both contain I as a set, but they might not even be comparable. And of course, these could be comparable and these not be, right? That's another possibility. So I expect this to be just, this is like a shotgun blast. It's just a big mess for sure. But it certainly is a partially ordered set. Right, is everybody okay with that? It's certainly, if you have containment, it's antisymmetric. Anything is less than or equal to itself, and it's certainly transitive, right? Okay, so to apply Zorn, we'll let C equal, let's see, RJ, IJ, J in some be a chain. Okay, so suppose we've got a chain, right? So we can apply Zorn, we need to show that this chain has an upper bound. We take the, well, I use the verb take. We claim that let's say B J is an upper bound. For C, where what are you supposed to is, yeah, the union of RJ and J is the same thing. That is, it's the union of respective ideals. Now, certainly, for all J and gamma, RJ, IJ is less than or equal to TJ. That certainly is true, right? Because each RI is contained in T, and each IJ is contained in J, just by the way that I've set this up, right? So it is an upper bound if that ordered pair is in. So the only question is TJ in gamma? Right? So that's the only question. Well, what was gamma? It's all such ordered pairs. So notice that. Okay, no problem there, right? Because a union, every RJ is contained in the quotient field, so its union is contained in the quotient field. So this is an overring problem. And of course, it's a union of rings, so it's a ring. That's another thing that I should probably consider. Also, J equals the union is, we need it to be an ideal. Okay, so let me talk about details just a little bit, right? So to be an ideal of T, J has to be a subset of T. And of course, since every one of these IJs is a subset of RJ, its union is a subset of the union of this. So everything's living where it's supposed to live, right? IJ is a subgroup, right? We've seen that, and that's precisely because it's a chain. It's a union of chains. So so J is a subgroup. It also has vacuum cleaner property because if alpha is in J, then alpha is in some I sub J, right? And if T is in T, then T is in I'm sorry, RJ prime. So we could go through the cases here, right? If RJ prime is contained in RJ, then T is in RJ and T alpha is in IJ, so it's in the union. On the other hand, if this one is the bigger ring, then notice that alpha is in IJ, which is contained in, it's also contained in IJ prime. Right? Well, yeah, if this is the bigger ring, then this is contained. RJ is contained in RJ prime. And so again, T times alpha is in this case, RJ prime, so it's in J, right? So is everybody buy that this is an ideal? What else do we need? We need it to be a proper ideal, don't we? Right. Also, J is proper as one is not in I sub J for any J. For all J, one is not in IJ, so it can't be in J, because that's right. Also note, I is contained in J. So it looks like what we have here is T is an overring of R, and J is an ideal. And notice that TJ is an upper bound for the chain C. So Zorn's law applies. So Zorn applies. And we have a maximum pair, which I will use the suggested notation BJ. Okay. Everybody okay? Now, it remains to show that, so now we've got this maximal pair, right? So what does this mean? This means that, let me remind you, R, D, K, and I, J, all right. I guess the last thing, I guess I really need to.
So why did we bother using pairs instead of just saying we consider the set of overrings that I survives in?
Because, so so let's go that route. I mean, if you consider all the overrings, then, what you're gonna do is you're gonna have a union of those. And that now survive. So the reason that I've always thought to do it this way is because the ideals can change, right? Because really what we have here is IJ, because in the overring, I itself as a set isn't an ideal, right? So, yeah, so here's logically what happens here, is if you just look at the overrings. So you start with R, you've got this proper ideal. And you certainly could,
This is
you
the
know,
overrings that I survives in.
yeah, so you look at the overrings that I survives in, but so what we're trying to do is, yes. Right.
Because that's what my first attempt would have been. And it seems that this same proof works for that.
Well, actually, let me get back to your question. Let's see, because what we still have to do actually is we need to show this valuation. All right, so, right. So here's what we have. So what we have is I survived in, um, not in any proper overing. Right. Um, okay, plain. B is a valuation domain. Okay, so, suppose U is in K. Now, to show the sums evaluation domain, let me, of course, zero is going to be in there. So let U be a non-zero element of K, we need to show that either U or U inverse is in V. Right? So, you know from earlier that J survives in either B U or B inverse. But DJ is a maximum pair. BJ is maximum pair. So J cannot survive in a proper override. Right, because J has to blow up in any ideal, or I'm sorry, any overring that properly contains it. So what does this mean? Well, that means that these two can't possibly both be proper overrings. So the U or the U inverse must be V, which means U or U inverse is NV. And there you go. Right, and of course, J is an ideal of V. So B. Okay, so good for us. We have that if you have a proper ideal of R in a domain, then there's some valuation overring in which that ideal survives. We can bootstrap this into, I consider, a very fundamental theorem for inequality. And it's actually, I mean, I'm still on my honeymoon with this particular theorem. It's actually kind of, and I've known it for a while too, so it must be true love. This is an amazing theorem. So let's let R be an integral domain, quotient field A. 6. Theorem. Let R be with quotient field then the integral closure of R so the integral closure of any integral domain is the intersection of all valuation overrings contained. This is astounding, right? Because valuation domains are these very nice rings that have this property that any pair of elements, one of them divides the other. What's that got to do with integrality? Well, this is the integral closure. So if you want to gather up all the integral elements, just look at everything that's in every valuation overring of R. Okay, so let's prove this. And we've got the tools in hand, and we're going to use this to whip out a couple of corollaries that I promised earlier. Okay, how do we prove the structure? This is the one that's a little bit easier, perhaps. What does this mean? This means that X so X is integral over R, which is contained in V, right? So X is integral over each V containing R, right? Because if it is a root of a monic polynomial with coefficients in R, it's certainly the root of a monic polynomial with coefficients in V, because V contains it. Well, what do we know about a valuation domain? Valuation domains are integrally closed. V, since valuation domains are integrable. So that takes care of that container. Right? Any X and R is an inner valuation domain that contains R. Or X in closure, I'm sorry. The other direction is a little bit more interesting. let's suppose, let's see, I guess this way. Now, suppose X is empty over R. Well, let me go back, recall X, oh, I'm sorry, suppose X is, in each valuation. Yeah, I've already done that one, now I'm doing this one, right? Recall X is integral over R if and only if X is in R X inverse, right? You remember that old chestnut we had a couple of times, right? Well, if X is non-integral, over R, then X is not in. Right? So if so we've got something that's in each valuation overring, if it's not integral, then X is not in here. All right, therefore, X inverse is a proper ideal. Rx inverse. And so there exists a valuation overring let's say call it W of Rx inverse, hence of R, right? Because valuation overring of R joined with X inverse is certainly valuation overring of R, such that X inverse survives. And and what's the problem with that?
X is not in W.
Or, but as X is in W, this ideal can't be a proper surviving ideal if there's an X floating around here, right? And there you go. So we just used that previous result for one second, but it's absolutely crucial here, isn't it? And it's amazing because it shows you the power of this, because this is all done, we talk about integrality, never in terms of polynomials. Right? Okay, any questions? Okay, I'm going to give you a corollary with two proofs. One from a previous result, someone a corollary out of two previous results. But ought to be any interval domain, then interval closure bar is interval closed. Another way to put this is R hat. So once you go to the interval closure, you're stuck. You can't get any new interval on this that way. Okay, here's old school proof. Suppose X is input over R bar. Right? So there's a polynomial. H R I R and
Right? Spanish, RILs.
sort of. That's the idea. Actually, note X is in fact integral over um, right? Because really, X is integral over this because really I don't need all of R bar. I just need these in elements, right? So this ring here, R n minus one is finitely generated and integral over R. Finitely generated is a ring and integral over R, correct? It's generated by those n elements, and each of these elements is integral, sums of products of integral elements are integral. So finitely generated, because they're only n things, and integral because sums of products are integral. So P is a finitely generated harmonic. We had a theorem that said if you're finitely generated as a ring and integral, then you're a finitely generated R module. So Tx is a finitely generated R module because X is integral over T. Therefore, X is integral over R. Gives us a finite module over R. Here's proof two. Any questions? Okay. Um, if B is a valuation over R bar of R. So if you have a valuation overing of R, then B is a valuation range of R bar. By this right here, because the valuation overrings of R bar are precisely ones over B. So R bar bar is the intersection of B such that, and the valuation overrings of R are the same thing. It's the valuation overrings of R bar. So the intersection gives me input. Okay, any questions on that? Okay, let me give you, I'll make the sort of verbal observation here. That every overring of evaluation, you're gonna prove something. Yeah, stronger. Every overring of evaluation domain is localization to homework. Any overring of evaluation domain is in fact evaluation domain. That's easy actually to prove from the definition. But again, that's kind of an interesting thing. Good domains sometimes have that property, right? So if you look at overrings, once you hit the level, once you start hitting valuation domains, it's valuation domains all the way up to the quotient field. The same is true for proofer domains. If you go up and you hit a proofer domain, it's proofer all the way up to the interval closure. So at long last, although I did say it in homework, let me tell you the definition here of what evaluation actually is. Let K be any field, field evaluation on K is a function V from K star, and by that I mean K with zero exclusion, into E, where G is a totally ordered abelian group. So it's an abelian group that has some sort of measure of ordering on it. For example, the integers, or the real numbers, or the rational numbers even. Satisfying for all A, B, and K star. One, the value of AB is the value of A plus the value of B. And two, the value of A plus B is greater than or equal to the minimum of the value of A, value of B, if A plus B is not zero, where the value is not defined. Right. By the way, some people actually define evaluation on the total field and what the value of zero be infinity, and they'll say this is a totally ordered group union infinity and value of zero is infinity. You can do it that way, and it does smooth out some things. It's like, so let me give you this final theorem. Let K well, that's something here that I've already done. Let K be a field with some valuation V. By the way, let me point out valuations always exist. You certainly have the trivial valuation, right? It takes every element here to the zero element group. Let K be a field with valuation V. Now, of course, that's a map into a totally ordered abelian group. Then V, which is the set of X and K, such that value of X is greater than or equal to zero, but this is a zero element group. Union the element zero is evaluation of. And this is sometimes associated with value V. and any valuation domain is actually formed this way, or it can be formed. Okay, any questions on that? You've got to prove a bit of this in the next homework, but we'll discuss this a little bit next time. Questions? Any questions? All right, let me remind you all that this week I have a visitor in town. He won't show up till Friday, actually, but he is going to actually give a guest lecture on Friday, and it should be very interesting. He's going to talk about, he's going to talk more about monoids, but there's connections to factorization. It's certainly commutative algebra. It's just he usually only uses one operation, but it has lots of good applications to it. So, all right, I will see you all on Wednesday.